Hi everybody, this video is by Miss Turley, and I'm going to walk through the notes for Unit 8 on kinetics about concentration versus time. In this video we are going to continue to apply the idea of rate laws and different order reactions, but we are going to start looking at how that is graphed and what we can learn from these graphs. So we are going to take a look at what happens when we graph the concentration of our reactants versus time. If we graph these reactions, we're going to notice that they look different depending on what type of overall order the reaction is. If you remember, we talked about determining the overall reaction order based on looking at the rate law and those exponents that each reactant is to. So we might see a 0 overall reaction order, a first overall reaction order, or a second overall reaction order. There are more options than that, but those three are what we're going to focus on for this data. Based on the overall order, we can actually write equations that can be used to determine what the rate is at any point in time. This is what we've previously been doing by drawing tangent lines, but we're going to actually look at equations that we can use to calculate them. And this is actually coming from calculus. They're called integrals. And so where these equations coming from is a little bit more than what we're going to go through, but we're going to look at how we can use them. So this is an example of a zero order reaction. And if we look at this data of concentration on our y-axis versus time on our x-axis, we see that it is a linear relationship and that it's a straight line as the concentration is just continually going down at the same rate. The rate is really what our slope is. And it's not dependent on the concentration. So we could say that the rate is equal to a constant, k. And for this graph, we could actually find that constant. It would be the slope. For a first order reaction, if we plot the concentration over time, it's not linear because we see that it is going to slow down as some of the reactant is used up. So we can also say that your rate is equal to some constant, but times the concentration of our reactant A, so that as A is consumed, the rate slows down. Using calculus, you can find the integral of that graph, and people obviously did this and came up with this equation. We notice that we have some natural logs here. And this equation, if we break it down, allows us to calculate the concentration of A at any time during the reaction. So this is saying that the concentration of A at time t, so whatever value for time you're plugging in on this side of the equation, this would be that resulting concentration at that particular time. So say at 5 seconds, if you plugged in 5 seconds for the t, this would be whatever the concentration was for A at that time. So the natural log of A at that time minus the natural log of the concentration of A initially. This little sub-zero means what the concentration started as, equals negative k, k is the constant, times t. If we look at this, we can actually put this into y equals mx plus b form, and then we can understand how we're getting a linear plot if we graph the natural log of A at time t on the y-axis and t on the x-axis. So here is a graphical representation of that. This is showing just the regular concentration of A versus time. Okay, so this is what you would collect in the lab for data. And then here, for each of these concentration data points, the natural log of that value has been taken. So this would just be done on the calculator. And we notice that this is a linear line now, and we can see how this is y equals mx plus b form up in this equation. We move natural log of A at the initial time to the other side of the equation, and now we're seeing y, what's on our y-axis, the natural log of A, equals negative k, which would be our slope, times t, which is on our x-axis, plus natural log of a at time 0, which would be our b value or our y-intercept up here. So why this can be helpful is if we have some concentration versus time data, if we want to determine is this a first order reaction, you can plot the natural log of a and see if that is a linear relationship. And if it is, we can actually calculate k by looking at the slope of the line, but it would be negative since this is decreasing. For second order reactions, there's a slightly different relationship. If we had a second order and had the regular concentration versus time data here, we could plot the natural log of it to see if it's a first order reaction. We see, nope, it's still not linear. So it happens that second order reactions create a linear relationship when the inverse, 1 over the concentration of A, is plotted. And actually we see that this is a positive slope, so our k value is just going to be the positive slope. Once again, this equation is very similar to the ones for first order, but instead of having natural logs, we have this inverse relationship of the concentration of A. A at time t still stands for whatever concentration at that particular time, and A sub 0 stands for the initial concentration of the reactant. So, to kind of sum up these graphs, if we graph the concentration of A versus T, and we see that it's linear right from the get-go, that tells us that it's a zero-order reaction overall because the concentration of A is not having an effect on the rate. The rate is constant. If we graph the natural log of A versus T, and if it's linear, that tells us it's first order, and we also could see that negative K, the negative value of the slope is equal to k, and if we graph the inverse of a versus time, if that's linear, it's second order, and just the value of the slope is our k value. Half-life is a specific application of a first order reaction kinetics, and as you've learned in earth science, half-life is the amount of time it takes for a substance amount to reduce by half. We often talk about this in earth science because of decay. Half-life reactions, just like nuclear decay, have first order kinetics, and we can use the equation for first order, which is the one with the natural logs, to find a half-life. Because we're talking about the amount of time that it would take for the amount of substance to decrease in half, we could plug in 1 for the amount at initially, concentration of A sub 0, and 1/2 for the concentration of A at time t. Then t will be equal to t 1/2, or what the half-life is. Because this ratio of A sub 0 to A sub t is always consistent, we actually have an overall formula that is on your useful info sheet for APCHEM. I think the bottom of this is cut off, but it says t 1/2, or the half-life, this is in time, so in seconds or in minutes, is equal to 0.693 divided by k. We're going to see why this equation works. So here's an example. What I want you guys to do is pause the video and try reading through this and answering it on your own. You can try to figure out, which equation am I going to use, and then what am I going to plug in. Then you can resume the video to look at the solution. Okay, so here's the solution to part A. Because it has told us that it is a first order reaction, which is actually going to be true anytime they talk about half-lives, we're going to use this equation with the natural logs. We have two different ways of solving this when it's asking for what the half-life is. We can either use this equation that's just what the half-life equation is, but I kind of want to show you why that works and how that works. We also can use this overall equation and just think about what half is. It told us that the initial amount of A was 0.05 molar, so I plugged that in for initial, and then I just said, okay, well, what would half of that be if we're saying what the half-life is, so when half of the time, or when half of it is gone. So half of it would be 0.025. In the notes slide, I had mentioned you could put in 1 and 1/2. And if you do all of these options, you're going to see that you get the same value of actually 0.693, which is where this comes from in this equation. Then we had a k value given to us in the problem, which was negative 0.271, which is what I'm plugging in, or it was positive 0.271, and I'm plugging in negative 0.271 into my equation. This T1/2 is what we're solving for, and that once again stands for what is our half-life, and in this case the units in the problem we're given were seconds. So we're just going to plug this into our calculator and plug in this to get a number and this to get a number and divide over to get our half-life of 2.56 seconds. You could also plug in your K value of 0.271 in here and you would get that same value using this equation here. Here's the solution to part B. Once again, we're using the same formula because we still have a first order reaction that we're working with. This one's a little bit trickier because we're having to solve for this value of what is the concentration after a certain amount of time. So we're solving within this natural log. We're plugging in that initial concentration at time 0 into here and our K value, and now we were given an amount of time after 5.12 seconds. So we can get out what some of these numbers are. So I multiplied these two and then added up this number to this side, and I have natural log of x at 5.12 seconds is equal to negative 4.3833. Now this is where, if you're comfortable with logs, this is going to make sense, and if you haven't learned about logs, you may want to come and chat with me more. But to solve for this value within our logs, we need to raise both sides to the power of e to eliminate this log. So this e raised to this is just equal to x, so then to this side we also have to do e raised to this value. So x is equal to e to the negative 4.3833, which is equal to 0.012 molar. If we pause to think about, does this make sense? We talked about an initial concentration of 0.05. Sorry for the interruption. This is what happens when I make screencasts in school and we have announcements. Okay, well, like I was saying, here is our final answer, which is a concentration after a certain amount of time, and it's less than the concentration that we started with. So it does logically make sense that our concentration should be decreasing as the reaction proceeds after 5.12 seconds. All right, I hope this was helpful, and take a look at some more practice problems in the textbook. Thank you. Bye.